All right, everybody, welcome to the KSP lecture, Solubility. We're gonna start with this warm-up problem. It seems like, you guys, yeah. Seems like the consensus was that this doesn't look familiar to you and we should just go through it together rather than sending you off to do the warm-up problem. Yeah, it's a nice table problem. It's theoretically what you learned yesterday, or the day before yesterday. This is page 12 of the notes. Okay, so what they want you to do, it's just a 3-liter flask contains 6 molar hydrogen gas and 6 molar chlorine and 3 molar HCl at equilibrium. This is they give you the reaction. And then they add additional HCl is injected into the flask. They want you to solve for the concentrations at equilibrium. So this is, it's sort of like a stresses problem about like shifting equilibrium and it returning, but really it's just math. What we know, because they give us these concentrations and they tell us that it is at equilibrium before the additional 15 moles is added, that we know basically the ratio of concentrations at equilibrium. We know what the KEQ value is, and we could calculate it. We might as well calculate it. Although if you think about this, you can just use the straight up ratios. There's going to be half as much HCl at equilibrium as there is either H2 or Cl2. We know that these ratios will be preserved, 6:3 or just 2:1. If you were to actually just solve for the KEQ, you would set up an expression with your products over your reactants. So concentration of H2, 6 molar, times the concentration of Cl2, also 6 molar, over the concentration of, oh, did I do that wrong? I think I did that wrong. Sorry, it should be products over reactants whenever you're doing KEQ. So the concentration of HCl over the concentration of H2 and Cl2. And we are including all of these, all 3 of them, because they are gases. If we had a solid or a liquid, we wouldn't include that, but 6 molar and 6 molar.
The 3-liter figure plays no part in the KEQ equation?
No, it does actually. When you have, yeah, when your products are gases or in aqueous solution, it does matter. So this concentration of HCl, it's 3 molar, but it's actually squared because we have 2 HCl. In this expression, we have the concentrations raised to their molar coefficients. So that's the expression for KEQ. Let's give us, looks like 9/16. Not 16, 36. I can do multiplication. So that would be how you calculate the KQ. It's not exactly necessary for this problem, but it's good to understand how to do it that way. So then what they tell you is that an additional 15 moles of HCl is injected into the flask. So they've added product, and according to whatever the law is. Does someone remember the law that you're talking about like it shifting? The Chatelier's principle, exactly, yes. So you've added product. So in order to return to these balanced equilibrium ratios, some of that, the reaction is going to proceed backwards and convert some of that product into reactant. So I think we want an ice table for this. Personally, sometimes I find ice tables annoying and unnecessary, but they can be useful. This will be H2. It's also been a really long time since I've done this. Cl2 and HCl. So initial concentrations, actually, so this is an ice table problem. When you have this sort of an ice table, the way they give you the equilibrium values first. So they start by saying 6 molar, 6 molar, and 3 molar. That's not actually the initial conditions. That is the conditions at equilibrium. I guess 6 molar. Yeah, I think we can do it this way. So
Wouldn't it be 2, 2, 1? You have 3 liters of the.
yeah, you could simplify the fractions. It doesn't really matter. It's a weird way. This is a weird problem to do with an ice table. You know what?
It would matter. Because from the initial to the each of the values, you add a certain amount. If you have a certain figure, like let's say 6 plus 0.3 is 6.3. 1 is 1.3.
Yeah, it might matter in terms of getting the actual correct calculations. You might be right. I'm just going to do this conceptually because I don't think this problem makes very much sense to put in an ice table. So when you add 15 moles of HCl, this is a 3-liter flask. So 15 moles divided by 3 liters is going to give you 5 molarity, which is going to mean that the molarity of HCl is now, instead of 3, it's going to be 5, or it's going to be 8. So that is maybe, at this point, I guess you could use an ice table and use these 8 and 6 and 6 as your initial values, and then use the KSP to give you your final values at equilibrium. But I'm going to do this slightly differently. This might or might not be helpful to you guys, but in this situation, because our ratios are so nice, we can actually sort of just think about this a little bit and do it with regular old math. We want in the end to have a 2-to-1 ratio of each of our reactants to the product. Right now we have 6 molar H2, 6 molar Cl2, and 8 molar HCl, which is going to be a total of 20. 20, it's a weird unit. It's 20 molarity, I guess, in your 3-liter flask, or 60 moles. But we can just now take this and divide it to figure out what the ratios are, right? Like if we want to have those same 2-to-1 ratios preserved, this can just be 8 and 8 and 4, right? There's like an algebra way to do that, but also just looking at it. So 8 molar H2, 8 molar Cl2, and then 4 molar HCl is going to give us exactly the same ratios between our reactants and our products. So those are the values that it will reestablish equilibrium at. You could definitely do that with an ice table too, but this is just kind of convenient in this case. So
How do we gain mass?
Because you added 15 moles of HCl. Did I do this? Oh my God, did I? I'm afraid I messed something up. Maybe I didn't. Yeah, I am. I was not expecting that this was going to be my responsibility to explain this problem, but what was that, Malcolm?
Isn't the only thing that relies on, or is like based on stoichiometric ratios, is the change and not the expected or sorry, not the equilibrium or initial values, right?
Yeah.
So you'll have values, you'll have molarity values for your equilibrium values that are not stoichiometrically related, but the change that they undergo is stoichiometrically related.
Yeah, and I think that's where I might have led you astray. Because it's 2HCl and Cl2 and H2. Hmm.
Want to give everyone a moment just to work on it together?
Do you all want a moment just to work on it? I'm not sure how useful that will be, but yeah, see if you can solve it with an ice table using the initial using initial concentrations from like after they've added the 15 moles. So 6 molar, 6 molar, and 8 molar.
Just do what I did. Same. I don't actually ever listen to lectures or pay attention. I never did any of that. I remember
Let's just say.
the only thing I ever did
I now have like
outside of class was watch
Let's say we
or
start with
review
15
lectures
moles.
before the test.
the webinar.
One time at 2 in the morning, that was it.
We'll start with
And it took me
15
about
molar,
10
6
minutes.
molar, say those are already.
And it was like 2 hours. Yes.
But the change from, I think the change from
Switch signs.
the. The
It
change
looks
from
awesome.
initial to equilibrium.
It's a triangle. I'll take you back to the tree house.
Only necessary to show you. what
The
the
man is.
Wait, so the comment okay,
You should probably not be basing what you're doing on my math because I'm not sure I'm right, but. And you did an ice table and you did it properly?
I did it based on the KEQ. I also did it
Charlie.
based on the KEQ.
Charlie,
Okay.
why don't we just start with, as initial, we start with 6, 6, and 3.
2, 2, and 1.
And then add 5 molarity to the HCl, and then do everything else based off that.
How would you? Do you think that would work? Does that make sense?
I'm not.
Well, it'd be 2, 2, and 1, and add 5, and we figure out that.
But didn't we say we're not gonna simplify it down?
Yeah.
Well, no, we have to add 5. It's important to simplify.
Yeah.
A over x squared equals 1. Because x squared, H2 and.
Yeah, if you have that, you're gonna also have.
And then eight. What do you get when you solve it that way? As the final equilibrium concentrations?
Oh,
Two polarity CL2 and one
I
ion.
love Daniel. I just wanted to play that.
Okay.
Well, I did it twice. I did it
Daniel's
twice,
awesome.
and then
I am
it
Daniel.
was CL. I actually did it first and then developed a split college that,
Maria,
as you can see in the match.
Did you end up with like 6 plus X and 6?
X is the change in concentration. So now it's gonna go more. It's like 50 moles of mercury.
Jay, is this sort of like 6 plus X, 6 plus X, and 8 minus X?
Minus 2X.
Okay.
So we do with 5, yeah.
Plus 2.5.
Sophia Melvin.
So are we both getting 4.5?
Actually, too good at it.
Yeah.
Did
I got those.
we're getting 4.5.
How did you do your thing?
You would say the things are due.
This is from.
How do you get rejected from the IB?
Yeah, I know. After.
Okay. Like, I don't think. I don't think it's.
So we did
Because you have 2 HCl in the KQ expression, you square the concentration. What? Yeah, it's this like molar coefficient. 4 minus 32 x plus 4x.
Six, we add one more.
Jay, I feel like I'm doing this wrong. Does it?
No, don't multiply it out. Do not multiply it out. Put a giant square.
Okay.
So we got this. Oh, that's right, that's right.
Okay. All right, let's come back together and look at this. I sort of think I remembered how to do ice tables. Um, this is right. This conceptual thing that I explained at the beginning is correct, and that makes sense. You'll end up with 8 molar, 8 molar, and 4 molar. The way you can do this in an ice table is to start with the concentrations that you'll have after you change equilibrium. And then you're going to, sorry, this should be a minus 2x. You're gonna,
What are we in second grade?
okay. Yeah, hang on. Yeah, it's recording. Sorry everybody about this messy recording. Yeah, so when you set up the ice table like this, you have too much product now. You have more, you added product. So the reaction is gonna proceed in reverse, and you're gonna be making reactant. You're going to, it's minus 2x because back in our equation all the way back up here, it's 2 HCl as our product. So for every, because we are converting product back into reactant to return to equilibrium. We want the moles to be in the same ratio as they were before, or our KEQ to be the same value.
We have a different value with the same ratio.
Yeah.
Yeah.
This is actually the much simpler way to do it with the thing I explained at the beginning is simpler in this case, but the way you'd set this up is X is your change. You're losing twice as much HCl as you're gaining of either Cl2 or H2. You end up with a molarity at equilibrium of H2 of 6 plus X, Cl2 of 6 plus X, and HCl of 8 minus 2X. You can set that equal to your KEQ, which from up here, I should have just seen that this is 1/4. It's 9/36, but that's 1/4. And then you can square root it and get 1/2 equals 8 minus 2x over 6 plus x. And if you solve that, you'll get x equals 2, which means the change is 2 molarity. You will lose 4 moles of HCl and gain 2 moles of Cl2 and H2. That was not a great explanation. I'm sorry. It took way longer than it should have, and it was very unclear. But
Is there a reason timer's on?
there's no reason the timer's on. I don't know who turned the timer on. Obviously took more time than I had. Oh God. Are you
Go to 0 and it'll go off.
okay? All right, timer is done. Let us move on. If I'm correct, you guys had a pre-lecture on solutions and solubility, a little review from unit 3, I think it was. Okay, some of you watched it at least. Okay, so let's get into our actual lecture. I need my iPad. Joy, can you just keep an eye on the clock and let me know if it's getting I don't know. Hopefully the right length.
I'll give you like a, I guess, warning.
Yeah, just okay. So, cool. You guys ready? Awesome. All right. Today's lecture is on KSP, which is a K value. It's basically a subcategory of KEQ. It's the equilibrium constant for dissolution for like solutions for the equations you get when you have a solid dissolving into water, basically in an aqueous solution. So the concept is that you have an equilibrium between the undissolved solid solute and the dissolved solute ions. You'll see reactions will generally be written like this. The forward direction is producing free ions. And the reverse direction is producing the precipitate or the solid version. And when you're at equilibrium, those are in balance. You're producing free ions and precipitate at the same time, and the concentration of the ions will be stable. So KSP, it's very similar to KEQ. There's just some sort of special quirks to it because we're talking about solutions and some special rules that you can apply. So when you're calculating the solubility product constant or the KEQ for a solution, KSP, you only use the concentrations of the free ions. And this is just because the precipitate is a solid. So it's a 1, its concentration doesn't matter. It doesn't have a concentration because it's a solid. So your expression will look something like KSP equals the concentration of ion A to its stoichiometric ratio times the concentration of ion B to its ratio. So if you were to write the KSP expression for this equation right up here, we have lead chloride dissolving into lead 2 plus and 2 chlorine minus ions. We're going to ignore, oh, that's not good. Mr. B's iPad's about to die. We're going to ignore the solid. Its concentration does not matter, and just use the products, which are R2 ions in the solution. So it will be
By the way, you might want to say the other one is one instead of this.
oh, thank you. They're not raised to the same power. These are different powers based on whatever their molar coefficients are. So KSP equals the concentration of lead 2 plus to the first power, or no power because there's no coefficient there, times the concentration of Cl minus squared, because in your dissociation you have 2 Cl minuses. Yeah, and these exponents, they're just coming straight from the molar coefficients. Okay. Cool. Theoretically, in the pre-lecture, you went back to this concept of molar solubility. Molar solubility is the concentration of a particular one of the products of the dissociation reaction, a particular ion in the solution with respect to its molar coefficient. So it's almost a metric of how much has dissolved rather than how much molarity is in the solution, because if you have like the concentration of Cl minus in this situation, you would take that concentration and divide it by 2 to get the molar solubility, because there are in your dissolution, I feel like that's the wrong word, but in the reaction, you are producing 2 Cl minus for every molecule that dissolves. So molar solubility, that should be a review, but it's good to go over it again. And then KSP is sort of similar. It's a metric of how much something dissolves, but KSP is based on the actual concentrations, just like regardless of their molar ratio of both products multiplied together. So these are going to be different values. They're based upon each other, and you can calculate one from the other, and we're going to be focusing a lot on that today, but they're different values. Okay. And multiplied together and raised to their molar coefficients. Okay. Like most KQ values, KSP is affected by temperature. So you won't just have the KSP for something, you'll have the KSP at a given temperature. But unlike other KEQ values, it can be said that KSP is affected by concentration. It's a strange concept. I'll do my best to explain it. Basically, the reason you need to know this is in case the AP asks you about what factors affect KSP. The way that concentration can affect it, it's like normally concentration doesn't affect it because the KSP is a constant based on the concentrations and the ratio of the concentrations at equilibrium. But because when you have specifically a solubility KEQ value, there is no denominator, and like you just have the concentration of the reactants. And in most situations, those will be constant because you'll have a fully saturated solution, and there's a given amount of ion that will be in that saturated solution. But if your solution is unsaturated and you do the calculations with an unsaturated solution, you will get a lower KSP value because both of those concentrations are going to be lower, and there's nothing in the denominator to cancel that out. They won't ask you to do calculations when the solution is not saturated, though. So it's just something to know. AP likes to talk about the factors that affect certain things, and KSP is a little bit strange because sometimes you can say that the concentration affects KSP. Generally, we say that if KSP is greater than 1, something is soluble, and if it's less than 1, which for some reason was not written in here, it has low solubility. That is not a very precise way to measure solubility, but sometimes you'll see that. Okay. We can actually calculate the KSP from the molar solubility of a substance, and there's a pretty solid chance you'll be asked to do that. So, I don't know if I actually got red. When you're asked to calculate KSP from solubility, you have to assume it's saturated. This is the same thing I was just talking about. If it's not saturated, you can't, KSP is about equilibrium with the dissolution, and if it's not saturated, it's just going to all dissolve and there won't be an equilibrium. So, or there will be, but it'll be different. I don't know. You have to assume it's saturated. The other thing that you can assume that's going to make this possible to solve is that the concentrations of both ions have to equal the molar solubility times their molar coefficient. So you're going to have if S is your molar solubility, you will have S molarity lead 2 plus and 2S molarity Cl minus in that saturated solution at equilibrium. And you can use that when you're given S or molar solubility to calculate what the KSP value is. We'll just do this first one together and then you guys can go off and do the next one or two. So they tell you the molar solubility of calcium sulfate is 8.4 times 10 to the negative 3 molarity. It's generally a good idea to write the equation, although this is a pretty simple equation. Also good to note that there will be a double arrow because this is an equilibrium. Ca2 plus and SO4 2 minus. It's just a one-to-one dissolution. This is a salt like this, or an ionic compound like this is considered an AB salt. There's just one of the cation and one of the anion bonded together. So, sure, yeah, sorry. So KSP equals concentration of calcium 2 plus to the first power, because there's no coefficient, times the concentration of sulfate to the first power as well. And we know the molar solubility. The molar solubility is just going to equal these two concentration values. So KSP equals 8.4 times 10 to the negative third times 8.4 times 10 to the negative third, which is just 8.4 times 10 to the negative third squared. And that is, I believe, 7.1 times 10 to the negative fifth. At least that's what I wrote down yesterday. In general, whenever you have an AB salt like this, where it's one-to-one, your KSP value will just equal the molar solubility squared. If you have something that is an A2 or an AB2 salt, it'll actually come out to 4s cubed, because you'll have twice the solubility. You'll have the A is just molar solubility, but this one will be twice the solubility and squared, because in that reaction you have a molar coefficient of 2 for this second ion, whatever it is. So that would multiply out to 4s cubed. Let's see, how many of these problems are there? Looks like there's 2. Why don't I give you guys like 5 minutes to do these 2 problems, and remember to pay attention to the ratios, the molar coefficients. Mhm. What was that, Trey?
How many more pages? We need like at least 15 minutes to upload the video because it's really slow.
Oh, okay. Let's see. These are a lot of practices. And, oh, let me pause the recording. I'm gonna pause the. All right. Let's come back and look at these. I didn't have time to finish it, so I'm not sure whether you guys did either, but we can at least get a start on this. For this first problem, this looks strange. This should just be whatever. So theoretically, you should have done a conversion and gotten a molar solubility of about 0.56. Is that what people got for molar solubility? Okay.
0.58.
All right. Yeah, rounding errors, but something like that. And then this is an AB salt. You're going to end up with the molar solubility times twice the molar solubility squared, or 4s3. You can write it all out, or you can just do 4 times 0.056 cubed. Oh, I wrote it wrong.
It's 200.
Yeah, You're absolutely right. It is 278, and I typed that into my calculator, and then I only wrote it as 78.
78.1. And then I got 0.015.
Yeah, 158.
0.0158 for your final answer.
For my molar
value. Yeah. Sorry, 0.0158 for the molarity of chloride. So then the molar solubility would be
That squared.
It was 2.5 to the -4 times 10 to the -4.
which we got.
That was, yeah, that's
Are you guys saying this is what the molar solubility value is? Or
Yeah. No, that's not the molar solubility.
0.01.
That is
0.0158.
yeah, that is the molar solubility.
that is the molar solubility. So then you take 4 times that cubed, right?
4 times. Wait.
Yes, this is
I
because
got 2 times that cube.
it should be 4 because you end up with 2s squared. It's 4s, 2s all squared.
Why are you multiplying it by 4?
So the KSP here is going to equal the concentration of the first ion, which is lead 2 plus. That's just going to be the molar solubility because its coefficient is 1, times the concentration of Cl minus, which is the concentration there is going to equal 2s because of this 2 here, and we have to raise it to that power. So 2s squared, which is s times 4s squared or 4s cubed. I realize my s's look messy.
Oh, so I did get that.
I'm still confused.
Yeah, where did the 4 and 3 come?
So when you square 2, you get 4. And then when you multiply s squared.
By s.
you get
Why
s
are we squaring?
Because it's 2s, you have 2 molar solubility.
Yeah, but why are we squaring?
Because chlorine, the presence of chlorine, or in lead chloride, there's 2 chlorine.
Yeah.
So you have 2 times the molar solubility.
So no, it wouldn't be Cl squared.
2 Cl squared, because you also have concentration, and then the
Yeah.
concentration is the molar solubility.
I thought it was the molar solubility to the power of its.
It is,
Yeah, that's good.
it's the actual concentration of each of the dissolved ions, which only equals the molar solubility when their coefficient is 1. So if it's more than 1, you have to multiply it by that. Okay, let's do this one more together, and hopefully this one will make sense. Ca calcium carbonate. Okay. Let's, huh?
To calculate KSP, don't you just multiply the molar solubility by
Hang on, can you guys be quiet for a second so I can listen to the question?
find KSP? You said that you multiply the molar solubility by each other and to the power of each of their coefficients, right?
Yeah, so molar solubility is basically as if all the coefficients of those ions were 1. It's almost a measure of how much of the starting thing dissolves. So the molar solubility is not actually going to be the concentration of that ion at equilibrium if its coefficient isn't 1, because for every mole of lead 2 chloride, we produce 2 Cl minus ions when it dissolves. The concentration of Cl minus is actually going to be twice the molar solubility.
I just don't understand why it's 2s squared and not just s squared.
It's because that concentration of Cl minus at equilibrium is not just the molar solubility. It's twice what the molar solubility is.
Yeah, but that's why we squared.
No, we square it because we have, so.
We square it because its effect on the equilibrium is twice what
Yeah,
something
then
with a normal.
we square, then we don't need to multiply.
So no, so you
No, you have
multiply
to
by
do both.
2 because you have 2 of them present in the compound.
You
So
have to
when-
square the
when it
constant, the
associates,
actual
you have
concentration.
2 times the molar coefficient of what is it, of lead chloride to start. So you have 2 times that amount. So you have 2s for chlorine, sorry. And then chlorine is also present at a 2
Molar.
Yeah, it's like 2 molar, so you have squared, because that's your molar coefficient is 2. So you 2s squared times s is 4s to the fifth.
Okay.
Okay, this next one actually is super easy. We don't need to go spend time on this. This is a binary salt, just AB. So the KSP value is the concentration squared. Or not the concentration, sorry, the molar solubility squared. And I think according to my notes, that's 1.3 times 10 to the negative 5. That seems wrong though. Yeah, that's wrong. I don't know.
About 3.7 times 10 to the negative.
That sounds much more correct. Okay, we'll go with that. I think I'm looking at the wrong notes or something. Anyway. This process, so this process, you take the molar solubility and you plug it in for the solubilities or for the concentrations of your ions, keeping in mind their coefficients. And then you just use that to calculate KSP. That's pretty simple. It's a little bit more confusing when you have to calculate it the other direction, when they tell you the KSP, but not the molar solubility. But we're gonna go over that right now. So this first problem here is going to have us calculate the molar solubility of iron 2 hydroxide. It is always a good idea to start with the equation. Iron 2 hydroxide is going to be FeOH2 because iron wants a 2+ charge and the OH is -1. Dissociates into iron 2+ and 2OH-. And then we're given the KSP. It's in this table somewhere. Looks like KSP is 4.9 times 10 to the negative 17. And that we can write our KSP expression. That is going to equal the concentration of iron 2+ times the concentration of OH-, and we're going to square that concentration because of the coefficient of 2.
Why is it then multiplied by 2?
Because the coefficient, the concentration of OH- is not the molar solubility, it's twice the molar solubility.
Yeah. Then why in the other one
Yeah,
is it
multiple.
squared? Why is it multiplied by 2 in the other one? This is the same situation.
It's going to be multiplied by 2. I put in the concentration of OH- rather than the molar solubility. So we're going to solve for the concentration of OH-.
Okay.
Or I guess I'll just plug it. I guess I could have plugged it in right there, but this 4.9 times 10 to the negative 17 equals the concentration of iron 2+, which is going to be S, times the concentration of OH-, which is 2S squared. This looks pretty familiar, probably. This is KSP equals 4S cubed. And then it's just algebra. All these KSP calculations are pretty friendly. At this point, divide by 4, S cubed equals 4.9 times 10 to the negative 17 over 4. And you can cube root that, plug it into your calculator, and S should come out to be 2.3 times 10 to the negative 6. Molarity is our molar solubility. I don't know if anybody wants to do the calculations and confirm that, but I did this calculation myself yesterday, so theoretically it's right. What was that?
2.3 times 10 to the negative 6 is about right.
Yeah. Okay. There are a few more practice problems here. Let's run through this one together because it's a little more complicated. This is an application of solving for molar solubility from KSP. It's not just solving that. We will have to start the same way though. They're asking what mass is dissolved in X milliliters of saturated solution. And we're going to have to know the molar solubility to be able to figure out how many moles are dissolved in that much water. So we can use our KSP from the table and we can calculate it for it. calculate for that. You can't just use the KSP because KSP is not a concentration value. It's whatever you want to call it, arbitrary constant or something. So silver bromate should be in this table up here, AgBrO3, and it's 5.3 times 10 to the negative 5. 5.3 times 10 to the negative 5. AgBrO3. They say bromate, which is clues us in that this is a polyatomic of some sort. I don't actually know what its charge is, so I will not be able to tell you what the charges of these ions are, but might be Ag2 plus and BrO3 minus. The only thing that really matters here is that this is a binary salt. It's 1-to-1. There's just a single mole of each ion in the salt. So this is going to equal S squared. It's going to equal the molar solubility, which is, so it's going to equal the concentrations of each of these ions, which are both the molar solubility. And because I was dumb and did not calculate this, if someone wants to square root that, that would be helpful, or I can slowly do it.
$0.007.
0.0073. Okay, 7.3 times 10 to the negative third, I think. Okay, so that's our molar solubility value. Now that we have that, that's telling us how many moles of silver bromate dissolve in 1 liter of water. We can take this is a molarity, throw in our units because those are helpful. We can take this and we can multiply it by 275 milliliters out of 1,000 milliliters being 1 liter. Basically, that's what fraction of a liter we have here. And then that's going to give us the number of moles. So then we're going to multiply it by the molar mass of silver bromate, which is something that you could theoretically calculate, but I'm just going to Google it. Um, 235.77 grams per mole. That is, and then you can do this calculation, and that will give you the number of grams of silver bromate that are dissolved in a saturated 275 milliliter solution. Cool. Let's see. Okay. I'm going to leave these 2 practice problems until the end if we have time. They're very similar to what we just did. Yes, sorry. This one. This one is similar to that one up there, and that we solved for the molar solubility. It was a simple calculation this time because all we had to do was set KSP equal to the molar solubility squared, and that it's an AB salt, and then use that solubility value to calculate for the number of grams that would dissolve in 275 milliliters. Okay, are we good? Good to move on. All right. Predicting formation in KSP. So when you know the KSP value and you're given a Q value or the current concentrations of the ions in your solution, you can use those concentrations to calculate the Q value. They call it QSP. it's the same Q value you've always used, but you calculate it the way you calculate KSP, which is just the concentration of the two ions multiplied together. And then you can use that to make comparisons. So if your QSP is less than your KSP, that means that there is less ions dissolved. There are less ions dissolved in solution than there would be at equilibrium. It's the same. It basically conceptually it works the same as any other Q value in that if your Q value is smaller than K, the reaction proceeds forwards. It's going to decrease. It's going to increase the concentration of the products or the ions until it reaches K or equilibrium. If your QSP is greater than your KSP, that means you've got too much product. You have more ions than you would have at equilibrium. Your solution is supersaturated and the reaction will proceed backwards, producing precipitate rather than ions. If your QSP equals KSP, then you're all good. Then you're at equilibrium.
And then QSP is like when it's not at equilibrium.
Yeah, QSP is the exact same expression. It equals the concentration of your first ion raised to its stoichiometric coefficient times the concentration of your second ion raised to its stoichiometric coefficient. It's Q if these are the equilibrium concentrations. If it's K, or sorry, that was totally backwards. It's Q if it's not at equilibrium. It's K if these are equilibrium concentrations and you're solving for KSP. Is my handwriting worse than Miss Judy's?
No.
I feel like it might be worse than Miss Judy's.
It's similar.
Okay. The change in temperature equilibrium. Yes. Okay, so we can apply this conceptually to predict whether a precipitate will form. In this case, they're asking about combining two solutions, 23 milliliters of 0.2 molar sodium carbonate and 12 milliliters of 0.1 molar magnesium chloride. This is a situation where you've got to remember that the solutions will be diluted by the fact that you're combining them. So we're going to end up with a certain molarity of Na2 CO3 that equals 0.020 molar times 23 milliliters out of the total, which is going to be 35. You're diluting it by this fraction, which is the number of milliliters of your solution over the number of milliliters of the total combined solution. I really wish I had like a nice calculator to do this quickly. Somebody want to do that and tell me what that is? The molarity of magnesium chloride is going to be the same calculation, but with its values. So 0.010 molarity times 12 milliliters, our initial amount of that solution over 35 total.
For the first one, it's 0.013.
Okay. Thank you. Yeah, that'd be great. Thanks, Sky.
Second one, 0.00.
003. Okay. Seems about right. Yeah. Okay. So now we can calculate the Q value because we have the concentration. So this is when I should have done this at the beginning, but we need to know our molar coefficient. So I'm going to write the equation. Sodium carbonate dissolves into 2 sodium ions and 1 carbonate ion. Okay. So Q, SP It's going to equal the concentration of sodium, which we just determined was 0.013 molar squared because of this 2, and then plus the concentration of carbonate ion, which is 0.003, no, not plus, sorry, times the concentration of carbonate. That is another calculation that somebody will have to do.
By the way, you have 5 minutes.
Yeah, we are close. 207. Yeah, Joy wants to stop the lecture, at least we have time to upload the video because it takes ages, and both of us have 4th periods, so we can't just hang out and upload it after class. Does anybody have that value for the QSP? While you're calculating it, we're going to have to know the KSP to determine whether we're at or below or above it. So
My
this is
question
just,
why'd you say 12 milliliters of
magnesium chloride in the,
aren't you? You're doing sodium chloride. Currently calculating sodium chloride.
it's magnesium chloride and
Yeah, but you use the 23 milliliters and then the 12 milliliters.
oh, hang on, you're absolutely right. I'm
It'd be both, yeah, it's the same, still the same.
just straight up doing this wrong, aren't I? Oh my God. Okay. So yeah, you're absolutely right. So both of these. Try. Do you remember how to do this?
I think you did it right. You just need to use 23 instead of 12 milliliters for the that's carbonate. Well, so for you calculated the concentration of carbonate in sodium carbonate, and then you calculated
Yes.
the concentration of sodium in sodium carbonate.
Okay.
But you have 12 instead of 20.
Yeah. Okay. So this is more complicated than I thought it was at first, and I'm sorry. I didn't realize that immediately. What we have here is actually, we're combining 2 solutions, and so we have a double displacement reaction. The question is whether one of those products is going to be in solution or whether it's going to be supersaturated and is going to precipitate. So the products of this are going to be, I guess I should write out the whole equation. Na2CO3 plus MgCl2 goes to AgCl. I think that's going to end up being 2 AgCl and Mg.
Yeah.
Sorry, you're right. 2 NaCl and magnesium carbonate. This is where it would be sort of helpful to know your solubility rules to be able to determine which of these is likely the product, or likely the precipitate. Helpful rule of thumb, though, is just that sodium chloride table salt is very soluble, so it's probably not our precipitate. The precipitate is going to be magnesium carbonate. So that's actually the equation and the equilibrium that we care about. MgCO3 with its ions, magnesium 2 plus and carbonate. So we can still determine the concentration of both of those ions. And basically, we're just going to use these concentrations. I think I was actually right with the concentrations I was using, and strangely, I might have just gotten the right answer.
You had flipped this, or the top one is seems to be 0.01. So you're calculating for carbonate, and there's 1 carbonate.
Sorry, where is that? What are you saying, Malcolm?
So you have the 2 different equations. One is calculating the
Concentration of
magnesium, and one is for carbonate.
But
Right.
if you did 0.02, which is 0.01, because you have 1 mole of carbonate for every mole of sodium.
I believe it's 1-to-1, so it would still be 0.2 molar. In a 0.2 molar solution of,
You start with different value. Okay, yeah.
yeah, in a 0.2 molar solution of sodium carbonate, you're gonna have 0.4 molar sodium and 0.2 molar carbonate. So you do have to sort of think about the molar ratios of these dissolving reactions, but in this case, they're both 1. There's 1 magnesium in every MgCl2 and 1 carbonate in every sodium carbonate. So we're good, and we can just plug these concentrations in. So the Q value for this dissociation, the dissociation of magnesium carbonate, is going to equal the concentration of carbonate, which is 0.013 molar, times the concentration of magnesium, which is 0.003 molar. And because we have no coefficients in this equation here, they're not raised to any powers. So this should be a pretty easy plug and chug there at this point. And then we're going to have to go look up the KSP value for magnesium carbonate in the table. You have to have the KSP value to be able to calculate this. So either they'll give it to you or they'll give you a table or something. Magnesium carbonate, right? Yeah, 6.8 times 10 to the negative 6th is our value. KSP equals 6.8 times 10 to the negative 6. And then does anybody have, well, I can do this in my head, I'm pretty sure. 3.9 times 10 to the negative 6th. Okay, 3.9 times 10 to the negative 5 seems closer. Okay, so our QSP value is bigger than our KSP value. That means we have more ions in solution than we would have at equilibrium, which basically means that those ions aren't in solution. They're forming a precipitate. So you will see magnesium carbonate precipitate here. And that took a while with all of my bumbling and that warm-up problem at the beginning that took way too long. But that is all we have to get through. There are 2 more practice problems here for calculating solubility and 1 more practice for predicting whether a precipitate will form that you guys could work on for the last few minutes, but we're going to end the lecture now.